Welcome to the satellite communication course. Now we start here with a satellite orbit. So we have seen that earlier last lecture. Our aim is about to learn about a satellite orbit. We have seen that LEO orbit earlier. That orbit means what? A satellite rotating in a space around the Earth there. Now based on the altitude, okay, if you calculate that, if you see that based on altitude, there are the types of orbit that we can say LEO Earth orbit. Then we can say that mu Earth orbit. Then we can say it is about a geo Earth orbit. Now that orbit means what? It is nothing but a that period of a satellite. Okay, you can say that rotation time or one revolution time. That is nothing but one particular orbit, and that each and every orbit they have some particular height. They have some particular inclination. Okay, so now here these three types of orbit, which is LEO orbit, mu orbit, and geo orbit. These are based on the altitude. Next, we can define the satellite orbit that will be based on the inclination. Now, inclination means what? What will be the satellite? Whether that satellite is inclined, or we can say that is about a non-inclined. That orbit is a inclined orbit or a non-inclined orbit. Okay, so that's why we can say that here we say it is about a based on altitude. We can say here it is upon a based on inclination, and then again based on a eccentricity. Based on eccentricity means what? If that eccentricity value is a zero, then orbit becomes a circular. If that eccentricity is not zero, non-zero of eccentricity, means your orbit will be a ellipse. Means satellite orbits can be defined based on the altitude, based on the inclination, based on the eccentricity. So common orbits, some common orbit that are nothing but what we can say it is about a LEO orbit, then we say it is about a mu orbit, then we say it is about a polar orbit, then we can say it is about a sun synchronous orbit, then we can say it is about a geosynchronous orbit, and a geostationary orbit. Okay, so now these are about the various types of a orbit. These are the a common orbit that is to be used. So in the case of a LEO orbit, we know that that range, or we can say that the about altitude of a given orbit is from 400 to 1500 kilometer, and that orbit, LEO orbit, it is it can they are inclined one. LEO orbits all that they are inclined one, and they can be used for the communication. Okay, that we can say that that can be for the mobile communication, or they can cover the large area. Okay, or complete surface of earth, that using that LEO orbit. But how? So in that case we need to use a constellation of an orbit. So constellation of a satellite. So we need here a constellation of a satellite. Means what? A group of a satellite in a given orbit. There will be a multiple orbit. That is nothing but a constellation. So we can cover the large area using the constellation. Similarly, if you consider that a mu orbit, medium earth orbit, in that case, that height is about what? 10,000 to the 20,000 of a kilometer. But again, here we require a constellation. Okay, again, here to cover the whole the earth, we require a constellation there. That is about, we can say, a constellation of a satellites we require here. But as compared to the Leo orbit, it requires a large number of a small number of a satellite in a Mu orbit. And again, all these orbits, that Mu orbits, are inclined one. So we can say that more multiple number of satellites to be launched, so that that forms a constellation of the satellite. And then here, that altitude is low. Due to the low altitude, that period of a given orbit, period of this particular satellite, that will be of a around a 90 to 100 minutes. But in the case of this Mu orbit, that period is about what? A 6 to 12 hours. Okay, that is about a period. This one is a period of what? Period of a Leo orbit. And here, the period of the Mu orbit. Now, this period requires, for one revolution, it requires a 6 hour or a 12 hours. USA has designed their GPS system, and they are using this satellite present in a Mu orbit, and their period is about a 12 hours. And they have used a 24 satellite. They have used a 24 satellite, and out of the 24 satellite, they have the six orbital plane, six orbital plane. Okay, and they have the three spare satellite. They have the three spare satellite. If suppose spare satellite means what? That can be used for the other application. Okay, that can be used for the other application. Then next about a polar orbit. In the case of a polar orbit, we say that we have the we say this about our Earth, and for the given Earth, there will be a north and south here. So from north to south, there may be a orbit like that. So it will looks like that orbit will be looks like. Okay, that orbit will be looks like polar orbit, and that each and every orbit, they are separated by the 22.5 degree of a separation. Okay, that we can say that 22.5 degree, that separation of latitude. Okay, that is about it between these two orbits. Means total, if you consider that, if you cover complete Earth, so in a total, we require a total 16 orbits. Okay, it requires a total 16 orbits. Means we say that 16 orbit with a separation of a 22.5, so that the satellite will, okay, rotate around this particular Earth, and we require a total 16 revolution to cover this particular Earth there. So now, in the case of, we say here that separation in terms of a latitude, and if you calculate that geographical separation on equator, okay, geographical separation on equator, in that case, this one is about our equator. Okay, now this one is about our equator. So then these are nothing but one path and two paths. So that separation between these two paths in terms of a kilometer, if you calculate that using that equator length, okay, so it will be nothing but what 2501.8 kilometer. That much is about the okay. That is about the separation of this particular polar orbit. Next, we see that a sun synchronous orbit. In a sun synchronous orbit, so satellite scan complete Earth. Okay, satellite will scan complete Earth. Now supposed to be this one the Earth. Now from this here, we say there is a satellite point. This one is the observer point. Okay. So now it will rotate that. Okay, likewise, satellite will come again this particular point. Means it will just like it requires a circular orbit. Okay, means it is nothing but a circular orbit. But a sun synchronous orbit means what? Is a point on the Earth, the point on the Earth that, or you can say time, that satellite will appear at the same particular point. Okay, satellite will appear at the same particular spot. Okay, okay. If you consider in another way, suppose instead of a satellite, if you consider that here we have the Earth now, and that Earth is rotating around the Sun. Now this is about a Sun. Now at the observer, if you see that Earth, Sun will be on the top here, the top of our head. Then okay, your Earth is rotating. Axis we have. Earth will rotate again after 24 hours. That particular point will reach again. Means again, and that particular point means what we can say that uh, that particular sun will appear again on the top of our head. That will take a complete one day, and that day we can say that solar day, or we can say that according to the sun appears there. Okay, exactly at the same point, or we can say that satellite appear at the same time or same point at the same local solar time of that particular day, or as like we can say that it appears like a sun here, and that particular orbit is called as a sun synchronous orbit. Then a geosynchronous orbit. In a geosynchronous orbit, that satellite has a period equal to the equal to that of the period of that Earth. Okay, with Earth's rotational period, we say that a Earth rotational period that will be equal to the satellite period. Okay, that will be equal to the satellite period. The Earth rotational period and that satellite period is the same. Means we can say that the Earth, we say Earth is rotating around its particular axis. Okay, it will rotate around this particular, and it requires a 24 hours. And similarly, we say that a satellite is rotating around the Earth. Again, it takes a 24 hours. Earth is again taking a 24 hours. Satellite is taking again the 24 hours, and that orbit or that particular orbit we say is called as a geosynchronous orbit. That orbit is called as a geogram because The period of a satellite around the Earth, period of a satellite around the Earth, and the period of Earth around its axis are same, and we can say they are synchronized. Okay, that period, both the period are synchronized there. So that's why it is called as a geosynchronous orbit. Next, a geostationary orbit. Now, in the case of a geostationary orbit, that height we say approximately that is 35,768 kilometer. Means height means what? Altitude. That is about a altitude of a satellite. Altitude of a satellite, that is nothing but a h we say. And then if you consider that a geostationary orbit means that satellite looks like a stationary. Satellite looks like a stationary in the sky, in the sky to whom? To an earth station. And that earth station is presented on the ground. Okay, earth station present on the ground. Now what does it mean by that? Means that earth is there and we have again the satellite. This one is about the earth and we have the satellite here. Now both are this one we say it takes a one rotation. Now satellite will be rotating around the earth and earth is again rotating we say. But if satellite is rotating around its axis, it takes for 24 hours. And again this one is again it will take a rotating, okay, but it will not take rotating around that, it will just rotating in a orbit, it takes a 24 hours. For the given orbit, it takes a 24 hours. And Earth rotating around itself, it takes a 24 hours. Now the period is same. Now the word we say that Earth rotational period and the satellite period which is same. That is called as a geosynchronous orbit. Now it is about a synchronous, but the difference is what? From the Earth observation point, from this particular point, the satellite will looks like a stationary. It is fixed at that particular point. But how your satellite, that Earth is rotating, the same at the same time satellite is rotating. Means if you see that from the observer point, there is a satellite in the space here. This one is about a satellite in the space, and from the ground station, if you look for the ground station there, so satellite will looks like the same position. It is fixed. Now, whenever the when your Earth is rotating from what? It is rotating from the west to east, means towards east. Your Earth is rotating towards east. Okay, rotation of Earth. It is a towards east. So same way, your satellite is again rotating toward the Earth. Okay, the same way the satellite is rotating again the toward the Earth. Means they are synchronized. Okay, means their speed is synchronized here. Okay, that velocity, how what is the velocity of that Earth? Okay, that whatever the velocity of that particular Earth, how it is rotating, and the same velocity of this particular satellite rotating around the Earth. Means okay, so means we can say that it is rotating same. Means it looks like a fixed now. Okay, this is supposed to be, I am saying that this is nothing but a equator here. Now this point is rotating. Okay, this one is about Earth. I'm supposed to be, I say this is about a plane. Okay, Earth plane here, and from that it is rotating. Likewise. Now, if you see that a geostationary orbit, we say it is about that much height, but in general, what happened because of that shape of this Earth, it is not a circular. So then that height, that 35,000, is to be fixed. Whatever the kilometer height is there, it is to be fixed. But if supposed to be that satellite is rotating from north to south in a polar orbit, in that case, what happen? That altitude changes. Now, here in that case, that shape of that Earth, it is just flat here. Okay, this shape from the north side and from the south side, it is about a flat here. And only this particular at a particular equator, okay, it is oblateness here. And this one is about a flat here. Means if you see the apple, that shape of the earth is looks like apple, means top portion and below portion is about a flat one. But only that, okay, it's just like a big size. Okay. So this is a fix. And earth is rotating around it this axis from, okay, this is axis. So it will rotate toward the east here. Suppose I am saying toward this particular direction, it is rotating like. Now this is about our equator. Now the position of the satellite, or we can say that if a satellite is placed in a equatorial plane. So now this is about your equatorial plane now. So satellite is to be present on the equator itself. So that altitude, that height will be a fixed, okay, from this particular position. And if supposed to be, we say that if our ISRO is going to be launch a satellite, so they have to maintain that satellite position is on the equator itself or equatorial plane. To get that particular orbit, geostationary orbit, so that satellite should be rotating in a circular fashion. Only when it will rotate in a circular fashion, because we have the equator here, and that surface on this equator is a fixed now. It is not vary. But in the case of a north and south side, that surface is a flat. So height, if you see the matching the height, it will be difficult. If suppose I am saying that rotating the satellite in this particular way, so it is difficult. But if I say that rotating the satellite around this particular equatorial plane, so it will be easier now. I can say that this is about a equatorial plane now. This is about our equatorial plane. Now means satellite is to present at a equatorial plane. So if that orbit is supposed to be considered in north and south, so then there will be difficult to match the velocity, or we can say that match the particular period. So that's why the satellite is to be placed on the equator, so that you can say that that orbital period and a satellite period will be that Earth rotation period and a satellite period will be matched there. Uh, So if that satellite is present on this particular equator, then inclination will be zero. Means in a geostationary satellite, okay, in a geostationary orbit, we say that a inclination must be zero. Okay, whatever the inclination is there, inclination must be zero. Okay, so this one, that means what? Inclination means what? Inclination of orbit. So otherwise, what inclination? Okay, so inclination of a orbit must be zero. Since it is on an equatorial plane, so that's why that inclination will be zero there. And so satellite must be orbiting in the eastward direction in the orbit. Means our Earth is what? Earth revolution. Okay, you can see that towards east. Okay. Similarly, a satellite, okay, satellite must be orbiting in the eastward direction. It will be must be orbiting in the eastward direction, so that your satellite will looks like a, you can say, it looks like a fixed one. And because of that, satellite looks like a fix at that particular point, so that's why can be used for the communication, or you can say that it can be used for the broadcast application. So nowadays we say that we have a dish TV at home, so we looks like that satellite, it looks like a stationary, because earth station means dish TV at your home, that is nothing but a earth station. We are getting a signal from the satellite, so that satellite looks like a fix now, but it is rotating with the speed of that earth there. Okay, with the speed of the earth. And since that height is large, so then because of that large height of the satellite, so our coverage area of the satellite will be large. Okay, area coverage means you can say that a coverage area large. Okay, you can say that a large coverage area. And if you say the, it is about a geostationary orbit, so how much is the coverage area covered by this particular satellite there? It covers the 42% of the earth's surface. 42% of earth's surface. Okay, it covers the 42% of a earth's surface by this whatever the geostationary satellite or a geostationary orbit. So to cover the whole earth, then it requires only three satellite. It requires only three satellite to cover whole earth. And these three satellite to be located, it is to be located at 120 degree. This three satellite is to be located at 120 degree apart in the geo orbit. Okay, 120 degree apart in the what? In the geo orbit. So that we can say that whole earth coverage area can be possible. And then earth stations to be located between the latitude that will be less than the plus or minus 70 degree. Okay, we can say that earth latitude. So these satellites are useful for the remote area communication. If we launch this satellite, so this can be useful for the remote area communication, because this satellite is fixed. Because from the earth station, satellite looks like it is a fixed now, fixed position. So that's why we doesn't require no need of antenna tracking. Okay, no need of a antenna tracking. We doesn't require a tracking system, or it doesn't require the antenna tracking at the ground station. So because of no need of antenna tracking, so that cost of that earth station is a reduced. So you know that your dish TV, that cost is reduced because antenna tracking doesn't require them. But the only the drawback is that there is a large propagation delay, and that large propagation delay is about what? It is about a 240 millisecond, because that altitude is a high, satellite position is a high there. So that's why it is about a delay will be a large propagation. And then delay is large because of what? We can say that is about a long path. Okay, because that altitude is high, or because of that particular long path, they have the large attenuation. Because of that long path, large attenuation. Again, because of that long path, large attenuation, as well as again we can say that a carrier to noise ratio at receiver, that carrier to noise ratio at receiver is a low. Carrier to noise ratio at receiver is a low there. So, so while designing a link, satellite link, we need to consider that a earth station, that earth station antenna, as well as a transmitting antenna at a satellite, so that we need to design antenna in such a way that that will send the signal that will reach to the receiver, and a receiver can able to receive the signal with a higher carrier to noise ratio. Okay, but here you can say that there are the some drawback there. Okay, so that particular delay and all, that is about your drawback of the geostationary satellite. So we say that a earth station, whatever we can say, earth station we have designed, and we have mentioned that a satellite here. Okay, this is about our satellite here. So whichever the antenna is used in the satellite, that size of the antenna is to be large. Because of that large antenna, so then beam width, okay, we'll see that beam width will be narrow, and again narrow beam width or large. Okay, it is depending upon the size, or it is depending upon the applications. But we will have the large gain. Size increases, that gain will be larger. Okay, so that's what these are the applications, or these are the most uh, satellite in most applications that geostationary satellites are used in. Next portion we see that Earth eclipse. Now, a Earth eclipse, that eclipse occurs, that Earth eclipse occurs when we have a satellite. Okay, when we have a satellite, Earth and Sun both are on the same axis. Okay, they come in the same line, or they come on the same axis. Then eclipse occurs. Eclipse occur means what? There will be a shadow on a satellite. There will be a shadow on a satellite. So that's why due to the shadow, that eclipse occur. And then due to the shadow on the satellite, then whatever the solar panels are there, they will not be used in that particular period of a time. How much is the time of the eclipse, and what is the duration of that eclipse, and when that eclipse occurs? Okay, that we need to be study here. Now that eclipse means what? We have the a sun, then we can say that is the earth, and then we have the satellite. In that case, sun we have the earth there, there will be shadow. Okay, so that's why, because of that shadow, even if in this particular range, if supposed to be satellite orbit is there, or satellite is present here in this particular orbit, there will be shadow appear on this particular satellite there. Okay, now it is depending upon that what will be the we can say that orbit. If supposed to be, we consider that a geostationary orbit. In a geostationary orbit, we have the on the equator, okay, in the equator plane, that satellites are present. So for this geosatellite, So then, at what day or what particular period of a time that shadow occurs? So that is to be understood here. Okay. So means both the cases here that are the all the devices, all these sun, earth, and satellite will lie on the one line or on the one axis there. So this is that earth is actually generally what earth is rotating around the sun and satellite is rotating around the earth. Okay. Now in that case, this is about a axis of a rotation of a earth now. Okay, this one is about the axis of rotation of the earth. So if supposed to be that earth is rotating at this particular place, okay, supposed to be earth is here. So again that satellite is rotating around it. Earth is here, satellite. So in that case, a period of what we can say that eclipse will be a different. So now at this particular period on the same line, so that duration of this particular orbit, okay, around this. So duration of that eclipse will be a small. Okay, duration of the eclipse will be a small. So we need to find out for a geostationary satellite. So when that eclipse occur, eclipse occur means what? That will be we say that in the case of what a spring equinox, or we can say that is about the autumn equinox. Okay, that eclipse occur, or you can say that a eclipse occur between the period from what a 27th Feb using the calendar year if you calculate that to 12 April and 31st August to 16 October. So likewise, that is about we can say that uh, eclipse occurs and a duration of that eclipse will be a 10 minutes, or we can say that it is depending upon that duration of eclipse is depending upon that in which orbit that satellite is present. But if you consider that a geostationary satellite, then eclipse will be for the 10 minutes there. Okay, eclipse will be occur 10 minutes, or we can say that maximum duration for this eclipse 10 minutes, 5 minutes, or whatever the generally we consider that a one particular hour, or we can say that's about 60 to 70 minutes. That is about the eclipse. But that maximum eclipse occurs, and at this particular place, it is about around a 10 minutes. But at the equinox, okay, at this particular equinox there, on a 21st of a March, and we can say that about 23 September here. So what happened? That that duration of that particular eclipse will be of a 70 minutes. So the so what happened? At the time of a eclipse, so satellite not getting the sun, okay, that whatever the sunlight, and because of they are not getting the sunlight, the soul whatever the solar cell present in a satellite, okay, solar cell. Now this likewise solar cell, likewise we have solar panels we have. So solar cell will not be energized, or satellite is to be depend on the alternate power. So they have the batteries or fuel cells present in a satellite. So, okay, the batteries or fuel cells present in a satellite, so they will be depending on that satellite will depend upon totally on that particular whatever the storage batteries or storage cells used in the satellite there. So we could see here a Earth eclipse will draw a Earth eclipse of a satellite. That is about the Earth eclipse of satellite here. Now we can consider that a sun now. This one is about a sun. Okay. So this one we have say that a sun here, and we'll consider that this one is about Earth, and this is about a Earth axis. Okay, that is about the Earth rotational axis we say, and we have the satellite orbit. These are about the different satellite orbit, and then we can say that a Earth is there, and we can say that is about a satellite we have. So now the position is about a position of a satellite now. For example, we consider that, and this one is about a axis of rotation. These are about a satellite orbit. This one you can say that is about a satellite orbit. Now the duration of that particular sun, we can say that here this is about a duration for this. In that case, it start from the 27th Feb and end up to the 12th April. That equinox start from this. That eclipse start from the 27th Feb to the 12th of April. Now a point here that is about on the 21st of March, that we can say it is about a that equinox occur. Okay, that is about a on this axis everything that satellite everything will become on the same axis there. Okay, axis of the satellite, axis of the Earth. Okay, likewise, and there will be maximum eclipse. Okay, so that is about you can say equinox. So similarly here we have a 23rd September, and the duration of eclipse that is about a 31st August to the 10th of October. Okay, that's about a 31st of August and a 10th of October. And here it occurs on a 21st of a June, and here it occurs on the 22 of a December. Then. Okay, so now this one is about 27th Feb to 12 of a April here. Equinox 21st March. Here eclipse occur. We can say that about a 21st of a June or a 20 December here. Okay, so likewise. So that is about we can say a eclipse occur. That is about the Earth eclipse. Earth eclipse of satellite means there will be shadow on a satellite. There will be shadow on a satellite because of that Earth. Otherwise, straight away sun, if supposed to be sun will provide the light to the Earth. Sorry, satellite directly. But at some particular point or some particular day, that shadow occur on this particular satellite there. Now, if supposed to be that we can say that satellite orbit, and we can say that about Earth, that we can say that if it is the inclined one. Right? Try we say that is about it. If it is a geostationary satellite, then for this eclipse occur this way. And if we have the Earth axis is inclined there, we say, and what will happen to the satellite orbit from the whatever the side of the orbital plane around the sun here? If we can say that Earth axis is a inclined one, so in that case we say here this one is about your Earth and this one is a shadow, and that orbit is inclined. This one is about a, we can say it is about the inclined orbit. This one we can say it is the north, and this one is about, we can say it is about a south one. And this one is about a Earth rotational axis now. But what happened here? The shadow appears. This one is about a Earth shadow. This one is about a Earth shadow. If supposed to be a satellite orbit is likewise, okay, that satellite orbit is likewise. So then in only in that region, if that satellite is rotating around this, only in that region, that eclipse occurs. Okay, only in that region eclipse occurs. Now if we consider that Earth and this is about your axis, the shadow is there. Likewise, this one shadow, and you can say that if our orbit is a circular one, okay, that is about, you can say that this particular orbit we consider now. So in that case, a shadow will appear because for a geostationary satellite, it is a circular orbit. So that satellite orbit, if you see that